Before I begin, let's look at something. This is a Python program I wrote to basically compare 24-bit WAV files to 32-bit float WAV files. And I created these with this TASCAM Capture 8.6, which I bought just to do this. Rode doesn't have something similar, so I bought this. Okay. So I recorded using the Rode NTG1 microphone, which is a boom microphone plugged into it. I think I have it here somewhere. It looks like this. And I downloaded both the 24-bit and the 32-bit float. I wrote this program. Now when I run it, it's going to chart each file. So I'm going to run this program. And on the left side is a 24-bit WAV file of the Capture recording the Rode NTG1 boom mic. And the right side is the 32-bit float file. To me, they look exactly the same. And I've ran this on different frames of the video with different files. And wherever in the file that I look, I see the same. See, it's exactly the same. And these are basically 100 plots. So each one of these points is 1/48,000th of a second into, in this case, a 24-bit data word, and into this space, a 32-bit float data word. So I just wanted to show you this immediately before I go on the video, because I know I get many comments from people who don't watch the whole video. And, you know, if you want to tune out, that's fine. But this is the hard data, the hard charts right in front of you. I'm also looking at the data. Let's look at the hard numerical data. So in this little experiment, using FFmpeg, I took the 32-bit float source WAV file, sample of that, and I output it as 24-bit. And then in Python, I write out each value next to each other. That's what these are down here. So let me just get to the top. So this is the 24-bit data that basically that the TASCAM produced. And then I took the TASCAM 32-bit float file and I converted it to 24-bit. And as you can see, the numbers are exactly the same. Now, you could say, well, you know, it maybe in a different device's 32-bit file, excuse me, the numbers would not be the same because it captured different data. But in this case, it did not, and it wouldn't even in any other. But it's going to take some time to explain that, so you're going to have to bear with me. But anyway, just want to point out, it's the same data. 32-bit float or 24-bit data that comes from a microphone is the same data. I'm going to go into this topic of how 32-bit float works and what it means and doesn't mean in a later video. But for now, I'm just going to briefly go over the main things you need to understand why those files are exactly the same. Okay. If we take 24-bit float data coming from a microphone, I hope if I turn my pen, it's coming from the microphone. The voltage is coming from the microphone. We can read a voltage of 1 to 16,777,000, and I forget what, but whatever. So this is the scale that we can read from beginning to end, and this takes up 24 bits of memory. All right? Now, in floating point, the way floating point works is it too has 24 bits of memory that it uses, but in this case, it actually goes through the decimal points. So let's say it goes to 1 to, actually I should have researched this, but it doesn't matter. But the bottom line is it basically goes through these numbers that are to 6 decimal points generally of what the core value is. Then it takes the other. Let me erase that. Well, let me just bring it up. It brings the other. It adds another 8 bits, And what these 8 bits create is a scale. I'm just going to have to clear the screen. So the 8 bits basically create a scale of 1 to 255 markers long. So 1 to 256. Sorry, markers long. So it creates a scale, and then the 24-bit part of it places each value into this scale. That's why 32-bit equals 24 bits, because the extra 8 bits in 32-bit is only widening the scale compared to 24-bit if it's just like this, for comparison's sake. That's why if you look on those sound devices, website will show like 16-bit is 96 dB or whatever, and there's 24-bit, and then this 32-bit, and they'll show like 32-bit float. The reason there's so much here is it's using 8-bit to basically expand this into this. Now, like I said, it does have benefits in post-production, but it has no benefits in capturing your microphone signal because that's still going into 24 bits of significant information. So I hope that very quick, like I said, I'm going to do another video, but I just wanted to do a very quick explanation about why you should expect the files to match perfectly. And now for the left, let me just show you one more thing quickly. Now let's look at the two files from the TASCAM recorder, both the 24-bit and the 32-bit float in Adobe Audition. So this is the 24-bit. The float has a little F in front of it. So here you can see it says waveform audio 24-bit integer, and now I'm going to click on the 32-bit, and this says 32-bit floating point. Now look at this part here. I'm going to go back and forth. Do you ever see it change in even a microscopic way? No, because it's the same data. The only difference is the 32-bit float has scaled it differently. Same exact data. So I'm going to repeat for the millionth time. If Rode says it prevents clipping, if Rode said it increases the dynamic range that you can capture with your microphone, it needs to show actual data where this isn't true. The data that they've shown in their chart where they expand the waveform, that's using a condenser mic where the mic is already preamplified. It's a little more complicated, but it's still the same thing. It's basically just it's an idiosyncrasy of the DAW of what it's showing. It's not representative of any real mic data. Let me ask you, if the Rode devices don't actually do what they say they're doing, what does Rode owe the customer who bought the devices in the belief that they would? What I think will happen is Rode will backtrack and admit that it's gain assist that prevents the clipping, not the 32-bit format. Now, if you want to forgive them when they do that, fine. Really, I'm not here to bash their equipment. I'm here to stand up for good science. If they're going to publish specifications on their mics that say, 72 dB signal to noise ratio, then they need to respect that, okay? Their marketing team can't come in and just throw that out the window and make up any freaking nonsense they want. Okay. Now calm down again. To explain more about the 32-bit to 24-bit difference, I'm going to use a silly egg analogy. It's like your microphone can only lay 12 eggs at a time. Now imagine you're a chef. You have 2 containers or 24 places to put them, so it's never been a problem. You have 2 empty cartons, and you can only get 12 eggs at a time. Rode is now saying that's created a new 32-holder carton, which is much wider. Even if it could hold 32 eggs, which it really can't, and I explained, how would that make a difference to you? If you only get 12 eggs at a time, you have all the space you need for the supply of eggs. Because again, you have 24, we have 2 cartons that will fit 24 eggs. Now, sure, having a wider container is useful in the kitchen if you want to move eggs around, and that's sort of what I'm saying is that 32-bit float, yeah, it does have a use in post-production, but we're not talking about post-production. We're not talking about the kitchen, about moving eggs around. We're talking about boxing them up as you get them. Now, I hope I haven't confused you all over again, but again, in a follow-up video, I'm going to try and explain in depth more about how 32-bit float works, what it does, and what it doesn't.